Then for every mathematical point, we did an averaging such that now at every mathematical point, we can assign properties, average properties of material. So we have a continuum description where at every mathematical point, there is a material point. Except that this material point is a collection of a very large number of molecules that are centered around that point. So we have the continuum description. So if you consider a body occupying the space, is shown by V, then each and every mathematical point is occupied by a material point. And each point, material point, is a large collection of molecules of matter constructing the body. So actually, a material point is an infinitesimal volume of element that represents that material at the continuum scale. We also call this representative elementary volume. Now, then I would like to, at this scale, introduce the concept of motion. This is now the macro scale motion, not the previous one where we had particles. So at the macro scale motion, a body has a structure, has a shape and a form. And at any given time zero, you can identify the space occupied by that body, and the motion will take this body, deform it. Let me take a different color. So it will take it. Oh, it's not. Okay. It is take it to a new position, a new format, a new form. It's bigger than the original. It could be. It can expand. It takes a new at time t. It's the same body V, but then at time t. This is called motion. So motion can rotate it, can move the points of the body apart from each other in different directions. We take an inertial frame of reference. That is a frame of reference that is fixed to, for example, a star. So not on the Earth, because the Earth is moving. It's fixed in the space. So let's say it's fixed to a star. And then we determine what we call coordinates with respect to this frame of reference. So every material point of that body has a coordinate x, and I show that with capital X, with initial notation would be x, k. So that's the initial coordinate. We call this also the material coordinate, because these are the original coordinates of that material. And then this is taken by motion to a new point, that material point, a new position, sorry. So if we take a color, the same color almost, and then the new position vector is shown by small x and initial notation is like that. So every point has a new position. This is called motion, and the transformation that takes us from this x to this x, we call that motion. We show it here by F. You can show it with other symbols. So you can say that every spatial, every new position, which we also call this the spatial coordinate, every new position is coming from an original position x, and another parameter that determines it is t. So that's just a transformation. And this is as I said, called motion. Okay, is that clear? Those who are not used to solid mechanics, they usually don't like this. It's not what people are comfortable with if they are only doing fluid mechanics. And I shortly explain what's now the difference between fluid mechanics and solid mechanics. Between a fluid and a solid, sorry. What's the difference between fluid and a solid? Now, this vector then is called displacement. This is U. This is displacement. Okay? Now, so with having actually this F, we can have everything. All of that is now explained here, that the coordinate of material point at time 0 with respect to an inertial reference is denoted by capital X. The motion carries it to a new position at time t, coordinates x. You can write that this is small x is a function of x and t, and this is called material or Lagrangian coordinate, and x is called the spatial or Eulerian coordinate. And one may also define the inverse motion, because if you have this transformation, then we can say that if we find a material point at x, at this position x, and we know the time, then we can trace back where it came from. So that's the inverse motion. There is a major assumption here behind it. Anyone?
And the function can be inverted.
Yes, but there's a physical assumption behind it. The physical assumption is that a material point that was at any actually position or time, but let's say this one, can never break into 2 points, because then it's not invertible indeed. Or 2 material points cannot come together and form 1 material point, because then the motion is not unique. So this actually precludes fracturing. If you want to study fracture mechanics, you have to do something extra there, because then a point becomes 2 points at the point of fracture. Okay. So this is the inverse motion, knowing position at any later time, and the time we can know where it comes from. Then we also define velocity. This is the macro scale velocity, which is the time derivative of the motion, which is saying that you follow a material point and then change of position with time is the velocity. And you can also write it in this fashion. This is called the material derivative. That means keeping x constant. And given the fact that u was small x minus capital X, and the derivative of capital X is 0, then the FDT is also the same as du dt, the time derivative, material derivative of the displacement. Acceleration is the derivative of the time derivative of material derivative of velocity, and the second time derivative of the displacement. Yeah, as I said, dt is called material time derivative. So in material coordinates, the material derivative of any function is simply written as this partial time derivative. You can also write this in terms of spatial derivative, in which case we have to use this identity. This is based on chain rule of differentiation, where this is partial time derivative and this is partial spatial derivative. And this is the velocity, has to multiply that. I'm sure you're familiar with that formula. Okay. Now, then we define, as I said, we define the displacement. to be the new position minus the original position, and we will have deformation only if these u's are different for different points, if there is a gradient in u. If you have a rigid displacement, so this, for example, if it just rotates and then moves and rotates and moves, actually there is no deformation. There is displacement, but no deformation. This doesn't change. So the gradient of u will remain 0. Okay? The gradient of u becomes 1, sorry. U would be the same, delta u will be the same for the delta x's.
But the particle could have a rotational degree of freedom, for example. No?
Okay, but then these are material points, so it cannot have within the body at place have a rotation. It has like time and then move and then rotate.
But in the case of a fluid, I mean, this point represents a volume element containing many particles, many molecules.
Right.
And then this volume element, as a consequence of something external field or whatever, could in fact could rotate.
Okay, so for example, this is rotating.
And then you will need another variable to describe the general state. It's the kind of a spin or something like that.
Yeah, but that is then different. That means different points of that fluid rotate differently. But if all the points follow the same rotation, then there is no deformation. So if I have a fluid here, and let's say if I do this, the fluid doesn't move, no, there's no deformation. If the fluid moves around here, that means different points will undergo different motion. Then indeed the divergence of u, the gradient of u will not be identity, will not be equal to 1. So that's why we say there is only deformation if this gradient is not equal to identity, is not equal to 1, but 1 is tensorial notation is the unit tensor. And so this is a measure of deformation. It's called displacement gradient tensor. But we usually work with other measures of deformation. One of them is this Cauchy deformation tensor, which is the product of these displacement gradients. And now this is written only in the material coordinates. You can also define another deformation tensor only defined in the spatial coordinates. If you have rigid deformation, this is not 0, as I said, is equal to the identity tensor. So for rigid displacement or motion, then CKL is equal to delta KL. And therefore we define the strain tensor. And the strain tensor is defined such that it's 0 if there is no deformation. Because then if there is no deformation, this will be equal to that. Okay. We also call deformation rate tensor, which is the gradients of the velocity. And then they are added to make this a symmetric tensor. All of these are symmetric tensors. Okay, so these are some definitions. Some of you are already familiar with. An important element of these deformations is the Jacobian of the displacement gradient. Is the determinant of the displacement gradient. And if the initial volume dV0 changes to a later time to a new volume dV, then we can show that the new volume is this Jacobian times the initial volume. This can be proved. And in fact, we can also prove that the time derivative of this Jacobian is equal to the divergence of velocity, which is the dilatation. This is dilatation. So 1 over j dj dt is dilatation. Okay, so with that, we can also show that because the mass is indestructible and cannot be created, the total mass of an element remains the same after deformation and is equal to initial value. So we have this identity because of mass balance. I just showed you that dV is j dV0. So you replace that with j dV0. I cancel dV0. So we can show that rho at any later time is related through j to the initial density. So if you know the initial density, we should always know the initial state of a matter or a body if you want to solve any problem, then the deformation will tell us what the new density field will be. That's also known. Okay.
Can I just ask one thing about the F, so this transformation? I mean, so in general, this is a matrix, but
it's like vector.
Sorry, the combination that you take when you compute.
Yes, when you take the gradient, it's a matrix.
But you don't seem to distinguish explicitly between the symmetric and anti-symmetric part of that matrix.
Oh, definitely.
Sorry.
It exists. That's sure. Why we define this Cauchy strain tensor.
Yeah.
Strain tensor, which is symmetric.
Exactly. Yes. So that's symmetric, and then you get rid of the problem with the rotation we referred to before. Because in general, if you rotate an object,
still his
one place does this space and all the other places is space.
Yeah, in the
but
case
that's not
when you have rotation,
yeah.
The tensor is not symmetric.
Exactly, it's not. But that's by taking the symmetric combination, you get rid of that problem.
And one reason we like to work with these symmetric tensors, strain and deformation rate tensor, we make it symmetric. We define it symmetric. We take the velocity gradient and make it symmetric. The reason is that the stress tensor is symmetric, and therefore, in fact, we can show later the non-symmetric part will disappear. If a stress tensor is not symmetric, which can also happen for certain material, then all of this will become important and we cannot work with this only anymore.
Yeah.
Okay, so this was some definition of motion and the kinematics at the macro scale. So we go back to where we ended yesterday. We derived these conservation laws. And I've written that in this general form. This is conservation of mass, momentum, and energy, and balance of entropy. And depending on what you put in for psi, you put in for I, F, and G. For example, if you put in for psi to be equal to 1, then we get d rho dt here. Del dot rho v. What should be I for the mass balance? Can we transfer mass within the body, and this is a single body, through an imaginary surface? Can we have mass transfer from this side of surface to the other side without motion, without any movement at all, macro scale? It's not possible. So there is no, this is a convective transfer of mass. This is a conductive transfer of whatever is psi. So for mass I is 0, it's not possible. We said that this was for a non-decaying material, so we cannot put in mass from outside wall into the body, or you cannot take mass out of it. And if it doesn't decay by itself, then F is 0. And because of the conservation of mass, G is also 0. Actually, I should use this 3. So that gives us mass balance equation, and you can see that for momentum, we choose psi to be V, stress tensor, gravity, 0, and so forth. For energy, psi has to be, what should psi be? For energy balance? Yes?
B squared.
1.5 V squared, but that's only the kinetic energy.
So the internal energy?
The internal energy as well. So for energy, we should have, so for energy balance, energy, Microsoft is not cooperating today. No, energy, I write it somewhere else. Okay, that works. Then psi is equal to E plus a half of V squared. I is the stress tensor inner product with V plus Q plus the heat vector. Because if you have an imaginary surface within the body, because of stress tensor, because the contact forces, and if there is movement, the contact forces will transfer energy to each other. And then there is a heat transfer which is occurring even if there is no movement, that's the transfer of energy. And then from the outside world, we will have gravity working if there is velocity, and then you can have radiation. Okay? So that's the conservation laws. We can use the same form for the entropy balance. This time psi is S, the non-convective or conductive flux of entropy is phi, external supply of entropy, and the right-hand side is not 0. In case of all the other ones 0, here it is not 0. And that right-hand side is governed by the second law of thermodynamics, that they say that rate must be non-negative. So this is the entropy balance. Okay, so this is as far as we got actually yesterday. So we have to now introduce the constitutive theory for a few reasons. First of all, as I emphasized yesterday, I didn't say anything about the constitution of the material when deriving these balance laws from the molecular picture. And that's one reason. The other reason is that if you have these conservation equations, you give me initial conditions, boundary conditions, I cannot solve the problem. Because if you count the number of equations and number of unknowns, we have done that here. This is the balance law, momentum balance. That's one equation, 3 equations, which is a vector, so that's 4. Now, stress tensor being symmetric, I don't count it because for a stress tensor, I count 6 components instead of 9. There is an energy equation. This is an inequality, so it doesn't help. So I have only 5 equations. But look how many unknowns I have. Rho, V, the stress tensor, gravity is given, and then internal energy, heat vector, radiation is given, S is unknown, the flux of it is unknown, and B is given. So if you count all of this, you will have 19 unknowns. And with 5 equations, you cannot solve it. We need 14 extra equations. And they come from the fact that, yeah, we have to say something about how these are all related to each other. And that it depends on the material itself. How do we determine that or decide on that? Well, you can do it based on your own experiences. You say, yeah, look, I have this material, I have studied in the laboratory. If I impose a velocity gradient on it, it reacts and I experience forces, and I have shown that these forces are proportional to the velocity gradient. Perfect, then we write stress tensor is proportional to velocity gradient. Now, you have 6 equations there. That takes care of that. And you say, I also studied if there is a temperature gradient, I'll have a heat flux. Or I put a temperature gradient, there is no heat flux. I don't see any heat going from one side to other side if there is a temperature across that. It's a non-heat conducting material. Okay, now the Q is 0 for that material. So there is 3 equations there. And this way, you can obtain all the missing equations. Now, you have defined a material that you know. So in fact, a set of constitutive equations models a material. And conversely, if you have a material, you need a set of constitutive equations for that. Okay, so that's the philosophy of constitutive equation. Okay, so how do we go about this we are not in the lab yet. I'm sitting behind my desk. I want to develop an approach that is reasonably systematic, and I can get, at least what I can do, develop constitutive models. I can develop a set of constitutive models, and then later try to find out which material is represented by this constitutive model. That's one approach I can take. And in fact, that's what we are going to do today, but then we will link it to all the experiences we have from the... Now, in order to do this, in rational thermodynamics or rational continuum mechanics, Truesdell and Erringen were the pioneers in formulating this, Knoll and a few others. They have developed a set of axioms as guidelines. These are somewhat scientific philosophy, but somewhat common sense. You can disagree with it, we can talk about it, see whether you agree or not. In philosophy, there is actually a lot of discussion about this. Everything in the world is caused by something. If there is a tennis ball moving in the air, now its movement is caused by the hand, by the air, by this, by that. Is that so? There are philosophers who don't agree. So, that is open. But so the axiom of causality says that the motion and temperature of the material point of a body are the cause of all physical phenomena. That's a very strong statement.
Right, I disagree, for instance.
Okay.
Yeah.
Good.
What about chemical potentials?
Oh yes, obviously. No. Chemical potential is an effect. You can ask, how about the composition, so concentration? Then I say yes. If we have a concentration, then that is a cause also. But chemical potential is an effect.
I mean, why is then the concentrations are not part of that?
I am looking as a single phase, single material body.
Oh.
No, it's not. I fully understand it.
It's not the general action.
No. Well, it is. No, you can add here. Yes, I'm sorry. You're right. I should have said that. For example, if you are interested in electrical phenomena, you have to add charges.
Yeah.
And indeed, if you are interested in a material that's made of, composition is made of different materials, different molecules, and these molecules behave differently, interact differently, then you have to add concentration. That's correct. But, so these are the primary causes of the effects, and the effects are the stress tensor and the heat and energy, internal energy. They are all, we talked about it yesterday. When you start at the molecular level, what do you have? You have mass and you have position. So those are even the force F between two particles, even that is related to the distance between them and to the mass of the two particles. At least there is one equation for that. So everything is determined by that, and that's what this is. The response function. So we identify this F and theta as the causes, which is also interesting. These are usually what we can observe with our senses and instruments. We can measure them and quantify them. And then all the others, which are stress tensor, heat vector, internal energy, internal entropy, and the flux of entropy, there are effects.
Theta is the temperature, no?
Sorry?
Theta is the temperature.
Theta is temperature, yes, I'm sorry. And F is the motion. Okay, so these are determined by those. That's the causality.
Just a question, in the case of
Yes?
in the case of equilibrium system, so then no motion, you say temperature determines material properties, but and then as an effect you have the stress tensor, which would then become the pressure, I assume.
For example.
Is the pressure? I mean, but the pressure is not if you because you have three thermodynamic variables typically, so you can fix temperature, pressure, and then you fix the volume. So it would seem that that's an independent variable.
No,
Yeah, but
pressure.
they are related by means of the equation of state.
Exactly, you have equation of state. And for the...
Yeah, but I mean,
so actually I have no pressure.
the equation say at a given density.
Yeah.
Yeah? And that
So
given
if
density is a given motion.
So you must fix something else then.
No, I will derive the pressure.
Okay.
There is no pressure. There is no pressure here. Look at my conservation equations. There is no pressure. The only thing I have is a stress tensor. And it says that the state of stress within a body is a cause of the motion and possibly temperature, of course.
You have no density as a variable either.
No, because density is totally determined by motion. Rho J is equal to rho 0. And J is the determinant of the motion. So it's related to that. If you know the motion,
So
give me the motion, I can give you
It's
density.
determined by the Jacobian, no?
Correct.
Yeah, but rho 0 is then has to be specified.
That is my initial condition.
Yes.
Okay, but then initial conditions are also determining the observer.
Yes, sure.
Yes, but that's the idea. We have an initial condition, and then the causes will give you these effects. What will happen to that body that you have in your hand? That's the
Then in your general scheme in which you put forward all these evolution equations, you have to consider the constitutive equations plus the equation of state.
Now, the equation of state is a constitutive equation. I'll derive it. Just bear with me. Bear with me. At the end of the hour, we'll go back to this question. Okay, so then this is the axiom of determinism. This is also a very strong axiom. It says that those effects at any given material point, so here I have my material, at time 0, there is a coordinate, any point of that you take, what happens to that point is a function of motion of that point, temperature of that point, but also motion of all the other points of the body, and the temperature of all the other points of the body. Not only that, is a function of not the time you're looking at it, so this is the body I have, the motion takes it a later time to this new position. I'm looking at it now at time t. What has happened to it is a function of at any given point, and at that time is a function of the fate of all other points of body and all past times, not just the present time. If you look at take equation, Fourier's law. Fourier's law says the heat flux at any given point is equal to, is proportional to, with a constant, to the temperature gradient. Temperature gradient not 10 days ago, not a minute from now, or temperature gradient at that time. And also, temperature gradient means actually the heat flux depends on temperature of that point and the point next to it. So it depends on 2 points. So heat flux, it's very, very simple expression compared to what I'm saying here. If I had said the heat flux depends on all points of body temperature, then you needed, first gradient, second gradient, third gradient, and so forth, all the gradients you needed, because then you involve all the other points of the body. And if I had said it depends not only on the temperature gradient at that time, but temperature gradient what it was a minute ago, then you needed the rate of time change of the time derivative of the temperature.
And this is because it's a local theory.
It's a local theory, and this is not a local theory. So we write it in mathematical form in this fashion. We say any of those T, so this is T, the stress tensor, Q, heat vector, energy, S, and the phi, the entropy flux. Any of them at any given, for any given material point at any given time is a functional of the motion of all points of the body and all past times. So this belongs to all points of the body, and T prime is from time 0 until the present time.
And the initial X.
Yeah.
And of course, it depends on where you are, because it could be heterogeneous material, and depends on the time you are.
If I want to, for instance, conclude that the system I'm looking at is an ideal gas, how do I see that in your formulation?
Yeah, that means I'm going to derive that. I'm going to derive for a non-viscous fluid, an ideal gas, derive how this should be developed for that. But at this moment, I am proposing with this constitutive equation, I can model anything except electromagnetic and chemical processes. I can model any process. I can model any material, no matter how complex it is. It can be modeled by this. I cannot propose any more general constitutive equation. What more general can it be than saying that it depends on its motion and the motion of all the other points at all past times? To see that this is very general, then I go to the next axiom. It's called axiom of smooth neighborhood or just neighborhood, and axiom of memory or short memory. And that we do the following. We expand F and theta in a Taylor series around the current material point. Remember, we are writing this for a given material point. And this takes care of heterogeneity. So I expand this F and psi around the current material point. And that means I use a Taylor series. So this plus the derivative times x prime minus x. These are the vectors with the next one. I have higher order terms here. The second derivative, third derivative, I haven't put in there. So that means, and then you can do the same for temperature. That means, so psi is now written not as a function of fk of x prime, but fk of our current material point, the gradient of motion. You remember this is gradient of motion. The gradient of motion, the temperature, the gradient of temperature. And I can add higher order gradients here. Depending on how complex the material is, I need more and more higher order gradient. But for now, believe me, this model elasticity, viscous, viscoelastic, gas, ideal gas, they're all in here. Actually, more than that. Because we haven't, so we do this, this was for a spatial Taylor series. We can now expand T prime, which is all previous times, around the current time. So we expand them in a Taylor series around current time. So that means, for example, Fk of this becomes the motion of the current point, the current time, plus the derivative of motion. What is derivative of motion? Velocity. So that's velocity, and could be gradient, the time derivative of velocity, that's acceleration, and so forth. And we do the same for the, you remember, please let me go back. Remember we have here the motion of current point, all past times of that point, the gradient of motion of current point and all past time. So I'm going to expand all of these in terms of the current time, and the same over there. So if you do that, then you get the gradient of motion for all past times is written as the gradient of motion current time plus the time derivative of the gradient of motion. What's the time derivative of gradient of motion? Is the gradient of velocity. So motion, velocity gradient, this is displacement and velocity gradient. And the same I do for temperature. If I do that, so now I replace that general constitutive equation with this a lot simpler constitutive equation. That instead of depending on the motion of all points and all past times, it only has limited dependence on time and motion, other points. So the current motion of the current material point, its displacement gradient, its velocity gradient, its temperature gradient, the time rate of change of temperature, that dot denotes d theta dt, and the gradient of the time rate of change of temperature, the current point and time. So that's taking me a step forward. What we will do is the following. We take this and put it through the procedure. At some point we come up with a set of constitutive equations that tell us this is how the material behaves. For example, if it behaves as an ideal gas or a viscous fluid. And then we say, yeah, but this is, my material is not doing this, it's more complex. No problem. We come back here. What did we throw away? We have to put it back. That will give you a more complex material constitutive equation. Okay? So, there is another axiom, it's called axiom of objectivity. It says that how a material behaves must not depend on the observer. Make sense? So there is a material there. One observer is sitting on a train and moving around it and makes measurements. It makes other measurements. Velocity will be different, for example. And the other observer is just sitting next to it. So they will observe different velocities. That doesn't mean that the material behavior will be different. Therefore, only objective variables are allowed in the constitutive equation. What is non-objective? Now, velocity. You agree that velocity is not objective. It changes depending on the observer. Time is not objective. Because, yeah, you can choose your reference time. I choose a different reference time. You choose a different one. Do I start the experiment today to study this material? Do I study tomorrow? I should get different behavior. That's not possible. So time is not the spatial coordinate. Yeah, do I do it here? Measurements? Do I do the measurements somewhere else? That doesn't matter. It shouldn't matter for the material. What behavior of the material is.
Does this axiom applies to in relativistic theory?
No. For example, if you do it some other place and that other place has a different motion, like Earth or Moon, then it's no. This is all Newtonian mechanics. Okay, so dependence on time and the coordinate is not possible, and that means from, I should have written it here, from this list, this must go, because this is simply the position. This must go, it cannot be allowed, and time must go. So from those, only these survive as, one thing I forgot to say, this list is called the independent variables, and this list here are the dependent variables, okay, of the constitutive theory. The independent variables are variables we should usually be able to measure. Usually, if you solve a problem, you formulate your problem, solve it numerically, analytically, whatever you solve, you formulate in terms of these things. You never solve the problem in terms of stress. It's always in terms of deformation, or temperature, or density. Okay? So these are the constitutive, independent constitutive variables, and then we have dependent constitutive variables. Okay. And then we go back, we have these equations, balance law. So now we have the choice to say a stress tensor depends on not the motion, the displacement, the velocity gradient, temperature gradient, and so at the list I showed you. But then, how do I know a choice I make does not violate balance law, mass, momentum, energy, or the second law? That I have to check. So that's called axiom of admissibility. Any constitutive assumption you make must not violate balance laws and the second law of thermodynamics. And this has major, major consequences. So we need those from those balances that I counted earlier. These are 19 equations. I have only 5. These are not 5 equations. I have 19 unknowns. So I need 14 extra equations. And these are the extra equations that energy depends on. Remember, I had gradient of motion. Instead of that, I write the strain tensor, temperature, and temperature gradient. I do not include a dependence on time rate of temperature. There are very, very few materials with a thermal memory. I know perhaps some liquid crystals, I don't know what they are, but they have not been observed. So I haven't included that or the time derivative of temperature gradient. Stress tensor the same, and so forth. If you count 1 equation, 6 is 7, 3 here is 10, this is 11, 3 here, 14. I have enough equations, enough unknown. You give me initial conditions and boundary conditions, I should be able to solve the problem. But of course, this is not specified what form, so we need that.
The question of the state is in the stress tensor, no? Because it contains the equilibrium path.
Yeah, so once again, at this stage, if I look at my conservation laws, these are the only variables I have. Where pressure comes in, bear with me. I'll show you. It's not here. I don't need it. I don't need it if I know how T depends on these.
But T is
in fact, for solids, for example,
is the total stress tensor, including the equilibrium part.
Of course. So all, see,
then the state is included.
That's a good point. The entropy inequality says entropy production, net production must be non-negative, which means that it can be 0. And that's equilibrium. So then it will be satisfied. Okay? So in order to make my development simpler, we assume that the external supply of entropy is only related to the external supply of heat, energy, sorry. For example, radiation. This is actually, there are lots of papers on this that, why you can write this and support this through defining the coldness and now how the coldness becomes material that's cold becomes hotter and so forth and so forth. But this is almost assumed always in the rational thermodynamics. This is an assumption, it's a constitutive assumption. Remember, we are writing constitutive assumptions. We can make choices. So we can leave it as unknown and get some equations for it, but what is always comes out is that this includes Q over theta, and maybe other extras that at this moment I do not include them. So if I say that the flux of entropy is a flux of energy, heat divided by temperature, I put that into the entropy inequality here, and I meant to, no, so this was supposed to be, no, let's see. There, okay, bear with me. I want to do this. And then, okay. Yeah, all right. So, I have energy equation, and I have the entropy, and then for entropy, as I said, for here, no, here I put in, I think maybe it's, I'm getting tired now, we have to have a break. So we have Q over theta, QK over theta, and then K, and for B we have H over theta. So we take a break now, but I want you to think about the fact that I have entropy inequality and energy equation. Things like gravity and radiation, they are given. They will not play a role in the constitutive equations. I'm not requiring that. I just can show that that will happen. If I now eliminate H between these two, so I can take H from here is equal to this side divided by rho and put that in here, then I have a new entropy inequality. And I want you to do this on paper, see what you get. Okay. But maybe we take a break first.
Yeah, we'll be back